In the silence between the stars, the universe is hiding something. An invisible substance outweighs every galaxy you've ever seen. A force is ripping the cosmos apart faster than light dares to follow. Signals flash across billions of light years, then vanish. Even black holes, the great devourers, are caught breaking the rules of physics. This isn't just space, it's a vault of secrets. Tonight, we unlock 7 cosmic mysteries that could rewrite the story of everything. 85% of the universe is made of something we cannot see, touch, or detect, yet it is holding galaxies together. Without it, the Milky Way would fly apart. Astronomers call it dark matter, but here's the strange part: after decades of searching, we still have no idea what it actually is. So how can we be certain this invisible force exists at all? Stay with me. The answer lies in the ghostly fingerprints it leaves on the fabric of the cosmos itself. A spiral galaxy hangs in space, its arms curling outward in perfect symmetry. From a distance, it appears calm, almost frozen in time. Yet every star in it is moving hundreds of kilometers per second in their long orbits around the center. By the rules of Newtonian physics, that calm image hides a problem. The visible matter stars, gas, and dust does not create enough gravity to keep everything bound. At those speeds, the galaxy should have flung itself apart billions of years ago. This leaves a question that cuts to the heart of how the universe works. What is holding these vast systems together when the numbers say they should be unstable? In the early 1970s, astronomer Vera Rubin studied the motion of stars in the outer reaches of spiral galaxies. The expectation was that stars farther from the center would orbit more slowly, just as planets farther from the Sun move more slowly. But Rubin's data showed the opposite. Rotation curves, the plots of orbital speed versus distance, flattened out instead of dropping. Stars far from the center were moving just as fast as those close in, which should not happen if all that existed was the matter we could see. At the time, many scientists found this hard to believe. The results implied the presence of a huge amount of unseen mass surrounding each galaxy. To make this idea more tangible, think of a merry-go-round spinning faster and faster. If only its visible structure were holding it together, it would collapse outward. The same logic applies to a galaxy. Its visible components are not enough to maintain that high-speed rotation. Rubin's findings were only the first clear sign. The second came from looking at much larger systems, galaxy clusters. These immense gatherings, sometimes containing hundreds or thousands of galaxies, have gravitational pulls far greater than their observed stars and gas can explain. The galaxies within them move so rapidly that they should escape the cluster altogether. Yet they do not. The only way the clusters can stay intact is if there is far more mass than the telescopes can see. A third form of evidence came from light itself. In some regions of the sky, images of distant galaxies appear distorted or even multiplied. This happens because massive objects warp space itself, bending the paths of passing light, a phenomenon called gravitational lensing. By mapping these distortions, astronomers can trace where the mass is, whether or not it emits light. The results reveal sprawling halos of invisible matter enveloping galaxies and clusters. And then there is the oldest footprint of all, the cosmic microwave background. This faint afterglow, a relic of the universe when it was just a few 100,000 years old, carries subtle variations in temperature and density. Patterns in this ancient light only make sense if dark matter was already present, shaping regions where visible matter would later gather into galaxies. Even in the universe's infancy, its gravitational influence was imprinted on space. All these independent approaches, stellar motion, cluster dynamics, bent light, and the fossil radiation of the early cosmos point to the same conclusion. The majority of matter does not emit light, yet it defines the structure of the universe. Galaxies and clusters are not held together by coincidence. They are bound within vast, invisible scaffolds of mass that outweigh their visible parts several times over. Without this unseen framework, the Milky Way would unravel. The threads of the cosmic web would never have formed. We can map its fingerprints with remarkable precision, and yet, if we can see its influence in every direction we look, the puzzle only grows sharper. Why can't we see dark matter itself? Imagine waking up in a universe where, during the night, every particle of dark matter had simply vanished. At first, nothing would look different. The sun would still rise, planets would still circle their orbits, and the stars would appear fixed in their familiar patterns. But the balance holding those patterns in place would already be unraveling. The Milky Way's stars, freed from the gravitational grip of its dark matter halo, would begin to drift apart. Orbits that have been stable for billions of years would slowly open outward. The grand spiral structure would stretch, thin, and eventually scatter into isolated streams of stars. This change would not stop at our galaxy. The local group, the small cluster of galaxies that includes the Milky Way and Andromeda, would come apart. Without dark matter's pull binding them together, the mutual motions of these galaxies would send them coasting away from each other into the vastness of space. Across the universe, galaxy clusters, now loose collections of unbound galaxies, would dissolve. Their tightly packed cores would empty as their members escaped the weakened grip of gravity. Structures that took billions of years to assemble would fall apart on cosmic timescales. It is similar to removing the steel framework from a skyscraper while leaving the walls and floors in place. For a short while, everything might seem intact, but the structure could no longer support its own weight. In the cosmic version of that building, the unseen beams are made of dark matter. We cannot look directly at them, but without them, there is no architecture for the visible universe to cling to. Dark matter did more than keep today's structures intact. In the early universe, its gravity was the scaffolding around which the first galaxies began to grow. Just a few 100 million years after the Big Bang, it had already pulled the thin gas of hydrogen and helium into dense knots. These knots formed along intersecting filaments, giving rise to the sprawling, interconnected cosmic web we can still see in maps of galaxy distribution today. Gas alone could not have gathered into these shapes fast enough. It was too diffuse and easily heated by early starlight and radiation. Computer simulations match the universe we observe only when they include dark matter. Without it, the models produce a picture where galaxies take far longer to form and end up smaller, fewer, and more isolated. The vibrant, web-like structure spanning billions of light years in every direction vanishes from the simulation, replaced by a sparse scatter of faint galaxies that could never match what our telescopes reveal. And yet, astronomers have started to identify rare galaxies that seem to contain little or no dark matter at all. These outliers challenge a simple, uniform picture. If dark matter is essential everywhere else, how can these systems exist? Some possibilities suggest extreme gravitational interactions, where larger galaxies rip away dark matter from smaller ones, a process called tidal stripping. Others propose that the measurements of these galaxies' motions are incomplete, giving an inaccurate view of their true mass. There is also the open possibility that some unknown process has changed the local balance of visible and invisible matter in ways we do not yet understand. These cases stand out precisely because they are unusual. They reinforce the role dark matter plays in shaping almost every galaxy we know, by showing how strange the universe becomes when it is absent, which leads to the deeper question if its influence is everywhere. What is this hidden substance really made of? We have no photograph of dark matter, no direct signal, no laboratory sample. Its reality comes from the patterns it shapes in what we can see. Galaxies orbit too fast. Light bends where nothing visible lies. And the early universe shows its signature in ancient radiation. These are all traces, not the thing itself. The structures we study exist because something unseen holds them together, yet its nature remains unknown. If most of the cosmos is invisible to us, then we live in a reality built on foundations we can only infer, leaving open how much else escapes our sight. Stephen Hawking once made a prediction so shocking it sent physics into crisis. If you fall into a black hole, not only is your body gone forever, the very information that made you vanishes too. Quantum theory says that's impossible. Both can't be right. So which law of the universe has to shatter? This is the puzzle that tore at Hawking's mind for decades, and the answer may tell us whether the very fabric of reality stores every moment of existence. Hawking's most unsettling result was not simply that a black hole could devour matter. His equations suggested that the detailed quantum patterns making up that matter, the complete record of every microscopic trait, would disappear from the universe without trace. According to his calculation, once something crossed the event horizon, even the subtlest imprint of its identity was gone forever. To understand why this was so radical, it helps to look at how black holes were first described. In early models, a black hole could be fully specified by only three properties: its mass, its electric charge, and its spin. This idea was summarized in the phrase, "black holes have no hair." In other words, no matter what fell in a star, a planet, or a person, the object that remained could be described by nothing more than those three numbers. All other details, from chemical makeup to arrangement of particles, were considered irrelevant to its exterior state. Hawking's prediction clashed with one of the core expectations from quantum mechanics, that the evolution of any system is reversible at a fundamental level. In a quantum framework, if you knew the exact state of a system, you could in principle reconstruct it either forward or backward in time. Thermal radiation from a black hole, on the other hand, seemed to be the exact opposite, utterly random, containing no clues about what created it. A simple analogy makes the problem clearer. Imagine setting fire to a book. Its pages are reduced to ash and smoke. But in theory, the microscopic properties of those particles still encode every letter that was on the page. In principle, somebody with perfect knowledge could piece the words back together. Hawking's results suggested a harsher fate. The book would burn, and not only would the original words vanish, they would be erased from reality itself. No ash, no smoke, no trace to analyze. In the framework Hawking used, known as semi-classical reasoning, space-time around the black hole was treated as a fixed stage. Quantum fields played out on this stage, and calculations showed the black hole emitted radiation with a purely thermal spectrum, Hawking radiation. The particles created this way were utterly uncorrelated with anything that had fallen in. There was no mechanism to transfer the complex quantum structure from the infalling matter to the outgoing radiation. This meant, in effect, that once the black hole evaporated completely, the information it had swallowed was destroyed at the most basic level. That is not just a practical loss, but a violation of unitarity, the principle that quantum processes preserve information. Without unitarity, the mathematical foundation of quantum theory, its probabilities, predictions, and symmetries would no longer be consistent. The reaction was immediate and intense. Many physicists were unwilling to accept that a core pillar of quantum theory could crumble. They argued that something must be missing in Hawking's approach, some overlooked feature of black holes or space-time that would allow information to escape. Others took the result at face value, concluding that perhaps quantum mechanics itself would have to be revised. For years, neither side could produce decisive evidence, and the dispute grew into one of the longest-running theoretical battles in modern physics. By the mid-1980s, it was clear that the field faced a binary choice: continue defending quantum mechanics at all cost, which meant finding a way for black holes to return information, or accept that information loss was real and would require rewriting the laws of physics. But if a black hole could give back what it had taken without breaking the principles of quantum theory, how could that faint trickle of information ever be detected from the outside? In the midst of this long-running debate, a Canadian physicist named Don Page suggested a way to approach the question without ever looking inside a black hole. Instead of trying to probe the interior directly, he focused on what could be measured from the outside, the pattern of information in the radiation it emits. The key was to treat radiation not just as particles flying away, but as a statistical object with its own measurable quantity, entropy. Entropy, in this context, is a number that reflects how much is unknown about a system's exact state. A low entropy means you have a great deal of detailed knowledge. High entropy means the details are mostly hidden. If you could somehow monitor the entropy of the Hawking radiation as a black hole evaporates, you could tell whether the missing information was being preserved in that radiation or erased forever. Hawking's own reasoning predicted a very specific trend. As the black hole radiated away more and more of its mass, the entropy of that radiation should only increase. It would start near zero when the first particles escaped, then rise steadily until the black hole was gone, and then stay high. That permanent high entropy would mean the radiation carried no imprint of what went in, and the original information was gone from the universe. Page's alternative was very different. If the evaporation process is compatible with quantum mechanics, if it's unitary, then the entropy would not simply climb forever. It would grow in the early stages, when each emitted particle was still entangled with the black hole's interior, making the radiation look random. But at a certain point, now called the Page time, the trend would reverse. Past that midpoint, new radiation would share correlations with earlier radiation, letting each new particle act like a small clue pointing back to the original state. Over time, these correlations would make the entropy drop back towards zero by the end, meaning nothing was truly lost. It's much like reading a mystery novel. In the first chapters, every event raises more questions than it answers, so your uncertainty grows. But as more scenes unfold, earlier confusions are resolved, and the whole sequence of events comes into focus. By the final pages, you can reconstruct what really happened from beginning to end. Page's curve is the plot of that mystery, told through the changing uncertainty of the radiation. A central piece of this picture is quantum entanglement between what remains inside the black hole and what has already escaped. Early on, Almost every particle outside is paired with a partner still trapped within, so the outside appears highly disordered. After the page time, those entanglement links start to form between the particles already outside, building a hidden structure in the radiation itself. That shift is what allows the entropy to peak and then fall. The page curve became a litmus test for theories trying to preserve unitarity in black hole evaporation. Any viable idea would have to produce this entropy pattern. This standard made it possible to assess possible solutions without knowing all the microscopic details of black holes. Decades later, new methods in semi-classical gravity using concepts like quantum extremal surfaces and islands inside the calculation have produced a page curve from first principles for the first time. These results suggest that Hawking's original picture was missing something subtle but crucial: a mechanism for information to reappear in the outgoing radiation. With that, the paradox began to shift. The conversation no longer centered solely on the idea that information was lost beyond recovery, but on possible ways to protect it within a consistent framework. This opened the path toward broader ideas like holography and the strange possibility that the universe records itself in ways we're only beginning to suspect. And if a curve on a simple graph can hint at such deep truths, then perhaps other hidden patterns could reshape our basic ideas of space and time. What began as a direct challenge to quantum mechanics has become a crucial testing ground for uniting our theories of information, gravity, and reality. The shift from believing information was destroyed to suspecting it survives has reframed the problem entirely. Now the focus is on uncovering the hidden mechanisms that preserve it during black hole evaporation. As one physicist put it, this is where we need to look to understand quantum gravity better. Asking where lost information goes is also asking what space and time truly are, and where the universe keeps the record of everything that has ever happened. What if the most fundamental assumption in cosmology was wrong? For centuries, we've believed the universe has no special places, no preferred directions. But when scientists studied the cosmic microwave background, the oldest light in the universe, they found a clear alignment with our solar system. They nicknamed it the axis of evil. And if it's real, it shatters the Copernican principle that's guided science for 500 years. So, what's going on? How could a faint echo from the birth of the cosmos suggest that our location has anything to do with the way the universe is arranged? This light, stretched into microwaves over 13.8 billion years, should carry no memory of us, our planet, or even our galaxy. Yet something in that afterglow seemed to be paying us unusual attention. The cosmic microwave background is often described as the earliest picture we can take of the universe. It shows space as it was when it first became transparent. Around 380,000 years after the Big Bang. Before that, matter and radiation were so tightly coupled that light could not travel freely. As the universe cooled, protons and electrons combined into neutral atoms and photons escaped, imprinting a faint pattern of tiny temperature differences mere millionths of a degree across the entire sky. It is these variations that carry a record of the initial conditions from which galaxies, stars, and planets would eventually emerge. According to the cosmological principle, when you zoom out to the largest possible scales, the universe should look the same in every direction. Those temperature fluctuations in the CMB aren't supposed to point anywhere special. They are expected to scatter randomly, a soup of hot and cold spots that reflects no particular orientation. In the early 2000s, NASA's Wilkinson Microwave Anisotropy Probe or WMAP, set out to map the CMB with a precision no previous mission could match. Over several years, it scanned the entire sky from a position beyond Earth's atmosphere, free from the blurring effects of weather or pollution. When its data were assembled, they produced a full sky map that looked like a speckled, uneven pattern, something like an old wallpaper mottled with subtle reds and blues, each blotch marking a region slightly hotter or cooler than average. In principle, that cosmic wallpaper should contain no hint of favoritism in direction. But once scientists broke the pattern down into its lowest frequency components, what are called the quadrupole and octupole moments, they noticed that these large-scale variations seemed to line up along almost the same axis. Even more unsettling, that axis was closely aligned with the plane in which the planets orbit the Sun, a structure that should hold no cosmic importance. If true, that connection would nudge at the foundation of the Copernican principle, the guiding idea that our position in the cosmos is not special. The possibility that the largest visible structures were somehow tied to our own solar system's orientation ran against centuries of thought that the universe is isotropic when viewed from a broad enough perspective. In 2005, researchers Kate Land and João Magejo published a paper discussing this strange alignment. They gave it a name intended to capture both its mystery and its challenge to standard theory, the axis of evil. The label stuck, rippling through both specialist literature and the popular imagination. It transformed a technical statistical oddity into a concept that seemed to carry philosophical weight, tempting people to speculate about deep cosmic asymmetries and, for some, a hint that our vantage point might matter after all. For scientists, the naming was something of a double-edged sword. On one hand, it drew attention to an anomaly that might offer clues about the early universe. On the other, it risked overselling what could be an artifact, a quirk of measurement or analysis, rather than a real physical feature. The question now sat at the heart of the debate: was this eerie alignment a genuine property of the cosmos, or was it simply a flaw hidden in the data? Could the strange axis be nothing more than the universe playing tricks on us, quirks born from the way we observe it rather than how it truly is? The truth is, at the very largest scales in the cosmic microwave background, the data we have to work with is surprisingly thin. Astronomers break the CMB map into spherical harmonics, patterns that describe how temperature changes across the sky. The lowest order ones, called low L modes, are the simplest and span the biggest angular distances. But because the sky only gives us one set of these, we cannot average over many examples. That leaves us with only a handful of large-scale modes to analyze. And with so little information, chance alignments can stand out more easily than they would in richer datasets. Adding to this is a fundamental limit baked into the physics of observation cosmic variance. It's not a flaw in our detectors, but a statistical ceiling on certainty. With only one observable universe, we can never know if a pattern we see is common or rare in the broader cosmos. Large-scale alignments might appear special to us, but in a multiverse of possible skies, they could be entirely unremarkable. Then there's the fact that our own galaxy is sitting between us and the edges of the universe, radiating and scattering light across the microwave bands. Dust grains in the Milky Way emit at similar wavelengths to the CMB, and charged particles accelerate along magnetic field lines, producing additional noise. In the solar system, sunlight scatters off dust between planets, creating zodiacal light that extends into microwave frequencies. If even a trace of these sources remains when astronomers subtract the foregrounds, patterns could be skewed, Instrument design can also introduce structure. If a telescope beam is slightly elongated instead of perfectly round, or if its sensitivity drifts over time, these imperfections can imprint artifacts in the data. Small calibration mismatches can produce low-level temperature differences that mimic real cosmic features. To minimize contamination, researchers mask the brightest parts of the Milky Way before analyzing the CMB. But when you remove large sections of the sky, the remaining map is no longer complete, and the mathematics used to reconstruct the missing parts can generate false alignments. This curse of masking leaves a puzzle. The very act of cleaning the signal can create the appearance of structure. When the European Space Agency launched the Planck satellite in 2009, expectations were high that its finer resolution, broader set of observing frequencies, and improved control of systematic errors would settle the matter. Planck's measurements confirmed that an apparent alignment of the quadrupole and octupole modes was still present in the temperature data. However, the statistical weight behind it was not decisive. Depending on how the data was treated, the probability of such an alignment occurring by chance varied, making it unclear whether the axis had real physical meaning or was simply a fluke. A separate approach in 2016 took a step back from individual anomalies and asked a more general question: does the universe, on the largest scales, show any preferred direction at all? Analyzers of Planck data comparing thousands of possible spacetime geometries found no significant evidence for departures from isotropy. Within the uncertainties, the cosmos looked the same in all directions. So the debate narrowed. The axis of evil could be a statistical outlier, an illusion born of our single sky and the imperfect act of observing it. But questions remain, because if it isn't a true cosmic axis, there may still be something in those anomalies pointing toward physics we do not yet understand. The axis of evil stands as a test case for how science handles inconvenient results. The idea of a perfectly uniform cosmos is elegant, but observations must survive the noise and imperfections of real data. With only one observable universe, every measurement is both precious and uncertain, and patterns can mislead as easily as they can reveal. Whether it is a rare feature of the early universe or a byproduct of our instruments, the anomaly has pushed cosmologists to sharpen their methods. Missions like Lightbird and CMB-S4 may soon decide if this axis is meaningful or just a statistical mirage. In 1950, over lunch, Nobel laureate Enrico Fermi looked up and asked four words that still haunt scientists: where is everybody? With hundreds of billions of galaxies, each with billions of stars, the math suggests intelligent life should be everywhere. And yet, silence. No signals. No visitors. Nothing we can confirm. Why does our universe look so ready for life, yet feel so empty? Stay with me, because the clues we've gathered might change how you see the cosmos. And the leading theories are stranger than science fiction. Imagine trying to solve a case without ever having seen the suspect. No sketches, no footage, no name, just the knowledge that somewhere they might exist. The crime scene isn't a back alley or a single building. It stretches across the galaxy. That's the scale of the search when scientists try to answer the Fermi paradox. And like investigators with nothing but fragments, astronomers start by building a profile. What kind of evidence should we expect if another civilization is out there? The main profiling tool is something called the Drake equation. It's not a formula that produces one neat answer. Instead, it's a way of laying out all the factors we'd need to know to estimate the number of detectable civilizations. First, There's the rate at which stars form. Then, how many of those have planets? Then, how many planets can support life? And how often life appears at all? After that comes the leap to intelligent life, followed by whether it develops the technology to send out signals we could detect. Finally, the equation asks, how long do those civilizations remain detectable before going dark? Each term is a step in the chain from lifeless rock to possible interstellar neighbor. Over the past few decades, the first terms in this equation have become sharper. Space missions have shown us more about stars and planets than we previously imagined. But as we move deeper into the chain, the numbers blur. We still have no reliable measure for how often life starts from non-living chemistry. We have even less certainty about how long species survive once they can broadcast their presence. It's like a detective knowing the number of houses in a city, but having no idea how many are occupied, or when the lights might go out. This is where the work of narrowing down possibilities feels familiar to any investigator. Detectives start with a wide list of potential suspects, then eliminate them one by one with new evidence. Astronomers do much the same with probabilities. They trim away uncertainty about star formation and planet occurrence. And each time, the numbers point to more opportunities for life. The expectation of finding it grows stronger. One of the biggest leaps forward came from NASA's Kepler Space Telescope. By monitoring the faint dimming of stars as planets crossed in front of them, Kepler revealed that Earth-sized planets in the so-called habitable zone are not rare, they are everywhere. Almost every star seems to host planets, and many have conditions that, at least on paper, could allow liquid water, the Drake equation's earliest terms, once full of guesswork, now carry weight from actual data, but instead of resolving the paradox, this abundance makes the silence more pronounced. Picture a high-rise building with billions of apartments. Through the windows, you can see lights, you know there's running water, and the kitchens are stocked. Everything suggests people could be living there. Yet the hallways are empty, and not a single voice reaches your door. The more we learn about how many potential homes for life exist, the more puzzling it becomes that we haven't heard from any occupants. If our cosmic neighborhood is as full of suitable worlds as the data now suggests, then the absence of a signal starts to feel like a clue in itself, a deliberate gap in the record. Rather than pointing us toward the number of worlds that could support life, the investigation now shifts. The next step is to look for the faint marks life might leave behind when no one is speaking to us directly. When there's no suspect to question, investigators turn to the smallest clues: the smudged fingerprint, the trace of hair, the faintest residue left behind. Astronomers work the same way when the galaxy stays silent. Instead of looking for flashing beacons or starships, they search for biosignatures and technosignatures, traces that could reveal a presence we can't see directly. Biosignatures are the chemical footprints of life. On a distant planet, a certain mix of gases in the atmosphere, like oxygen paired with methane, could be a sign that biological processes are at work on Earth. This combination is maintained by living organisms because oxygen reacts quickly with methane and would vanish without a constant source. If we saw the same chemical balance on another world, it would be worth close examination. Other gases, like nitrous oxide or patterns of water vapor, could point towards something similar. But detecting these gases at interstellar distances is not simple. Light from the planet has to be separated from the overwhelming glare of its star, then split into a spectrum to search for the sharp lines that each gas produces. Even when we think we've found something promising, the data can mislead. The The strange dimming of Tabby's star once led some to wonder if a vast structure was blocking its light. It turned out to be clouds of dust. On the planet K218b, a detection of methane and other molecules triggered speculation about life in its atmosphere. But chemical processes not involving biology could produce them as well. A single piece of data rarely stands on its own. We have to confirm it from multiple angles. And often the first exciting lead fades into a more ordinary explanation. This is why new space observatories are so important. The planned Habitable Worlds Observatory will be designed to scan dozens of nearby, potentially habitable planets with precision that goes far beyond what is possible now. By isolating their light, it could check their atmospheres for those telltale chemical imbalances and do so for multiple targets in a systematic way. Each confirmed detection, if it comes, would add weight to the idea that we share the galaxy with other living worlds. But the standards are high. A biosignature isn't convincing unless it's strong enough to stand out from background noise, stays consistent over time, and matches no known geological or chemical process that could mimic it. This leaves a lot of room for uncertainty and a lot of false alarms. Techno-signatures follow a different trail. These are the traces of technology, from hypothetical Dyson spheres that capture a star's energy to tightly focused laser beams sent across light years, or the glow of artificial lights on a planet's dark side. Projects like SETI have spent decades listening for such hints in the form of unusual radio signals. None have held up to scrutiny. If any civilizations are out there, perhaps they no longer produce signals that spill into space, or they exist for only a short period before going silent. It's also possible they use methods we cannot scan for at all. Communication might happen at scales or through physics we don't yet understand, concealed entirely. Like a conversation in a locked room with walls we can't penetrate. The information could be there, but invisible to all of our instruments. The result is a growing pile of incomplete, sometimes misleading evidence. Our file isn't empty, but every clue demands careful testing, and most end up filed under inconclusive. If we can't find them with the tools we have to ask if the quiet skies are telling us about their absence or about the obstacles that keep them unseen. Every new observation makes the puzzle sharper. The galaxy contains countless planets that seem ready for life. Yet each promising signal fades under closer inspection. It raises the possibility that the barrier isn't just distance or time, but our own method of searching. We may be asking the wrong questions or assuming alien life would reveal itself in ways familiar to us. Missions like the James Webb Space Telescope and the Extremely Large Telescope will push our reach further. The case is still active, and the right investigator could find the detail that shifts us from wondering to knowing we're not alone. They last for less than the blink of an eye, but release as much energy as the sun does in days. They cross billions of light years, carrying whispers of everything they've passed through, from the densest galactic cores to unseen webs of matter between galaxies. These are fast radio bursts, and their origins range from the explosive birth of magnetars to environments older than our own galaxy. The strangest part, we can now track some of these to regions only 10,000 kilometers across. That's like spotting a DNA helix on the moon. In 2007, while going through old recordings from a radio telescope in Australia, an astronomer saw something that didn't fit any pattern. The data showed a single spike in radio waves, lasting just a few thousandths of a second. It was bright, sharp, and strong enough to stand out among hours of ordinary signals. Whatever caused it had already ended by the time it was noticed, and it left no clear fingerprint about where it came from. The problem was simple. You can't plan to watch something that happens at an unknown time, in an unknown place, and lasts less than the blink of an eye. Radio telescopes scan small parts of the sky in extreme detail. To catch an event like this means already pointing at exactly the right location, at the perfect moment. Miss it, and all that remains is silence. At first, some scientists thought it might be a glitch, maybe caused by equipment or human activity, signals from satellites, microwave ovens, or airport radar have fooled astronomers before. Others considered whether it might come from known cosmic objects like pulsars, rotating neutron stars that sometimes emit regular radio pulses, but this burst showed no repetition and no match to any catalogued source. The moment it was over, it was gone. What made the burst impossible to ignore was its sheer output. Rough calculations showed it released as much energy in a few milliseconds as the sun does over multiple days. That much power in such a short time is hard to explain with familiar astrophysical processes. If your eyes were sensitive to radio light, spotting it from Earth would have been like glimpsing a single camera flash from another continent in a storm. Then came an important clue: the signal's dispersion measure. Radio waves travel at the speed of light, but lower frequencies slow slightly when passing through clouds of electrons in space. This causes the pulse to stretch, with higher frequencies arriving first and lower ones arriving fractionally later. By measuring how much the pulse was spread out, astronomers could estimate the total amount of matter it passed through. The number was far too high for a source inside the Milky Way, pointing instead to an origin billions of light years away. If that was true, then this burst had crossed most of the visible universe to get here. Yet in the years after 2007, targeted searches found almost nothing new. These events seemed to occur at random, and their rarity made it easy to doubt initial claims. For a while, fast radio bursts were more an unsolved puzzle than a subject of steady research. That changed when new instruments began watching huge portions of the sky at once. Instead of concentrating on a pinpoint, they monitored broad fields continuously. The most notable of these was the Canadian Hydrogen Intensity Mapping Experiment CHIME, a stationary array of radio antennas that can observe large swaths of the northern sky in real time. Once CHIME began operating, detections went from one every few years to multiple bursts each week. Not only were new bursts appearing more frequently, but some also showed patterns that no one had expected. Among them were signals that repeated, suggesting that their sources were not one-time cosmic explosions, but objects capable of producing them again and again. And one of those would force scientists to rethink everything they thought they knew about what could power a fast radio burst. When astronomers first began detecting these bursts at a steady pace, many assumed they were all the result of single, cataclysmic events, collisions or explosions, powerful enough to destroy their source entirely. That idea held until an observation in 2012 showed something strange. The same patch of sky produced another burst months later. The signal had all the same characteristics as the first. It came from the same place. And then it happened again. This was FRB 151102, the first known repeater. Tracking it down took years. But eventually, the source was located in a small dwarf galaxy more than 3 billion light-years away. This galaxy was actively forming stars and had an unusually dense, magnetized region surrounding the burst location. The magnetic conditions were extreme. far beyond anything that could be recreated in a laboratory. For many researchers, that pointed toward a young magnetar, a type of neutron star with an exceptionally powerful magnetic field, as the likely engine driving the bursts. The repetition itself posed a problem. If a fast radio burst came from a single explosive event, like a neutron star colliding with another massive object, the source would no longer exist after the first burst. But FRB 112-102 fired repeatedly over months and years, ruling out any one-off destruction scenario. The environment around it also distorted its signals in a specific way. The bursts were highly polarized and underwent strong Faraday rotation, meaning their polarization angle twisted as the radio waves moved through magnetized plasma. It was like a radio transmission trying to cut through a storm of charged particles, making the signal spin as it traveled. As Chime ramped up its observing schedule, detections of repeaters became more common. FRB 18-916 stood out not only for repeating, but for doing so with remarkable consistency. About every 16 days, it would produce a series of bursts, following a predictable cycle that could be marked on a calendar. This kind of regularity hinted at some underlying orbital or rotational process controlling the bursts. Then, in October 2022, astronomers managed to pinpoint an FRB's position with extraordinary accuracy. FRB 2022-1022A was traced to a zone just 10,000 kilometers across, roughly the size of Earth, inside the magnetosphere of a neutron star. This level of precision was possible because the burst was so bright and repeated in ways that allowed for precise triangulation using multiple telescopes. It showed that in some cases, scientists could locate the exact neighborhood of a burst's origin, not just its host galaxy. Yet the pattern was not as simple as all repeaters coming from young, magnetic neutron stars in star-forming galaxies. In early 2024, FRB 2024-0209A broke that assumption. This repeater wasn't in a region teeming with new stars. Instead, it sat far from its galaxy's center, inside an old, massive elliptical galaxy. Even more surprising, the data suggested it might lie in a globular cluster, a dense, spherical collection of ancient stars, billions of years older than the Sun. That environment is hostile to the birth of young magnetars, raising questions about whether other objects, like accreting black holes or unusual binary systems, could also produce repeating bursts. Each of these discoveries added a layer of complexity to the FRB puzzle. The range of environments, from chaotic star-forming galaxies to ancient clusters, showed that no single origin model could explain them all. And as these strange signals continued to be traced across the cosmos, scientists began to see them not only as mysterious one-off events, but as tools that could unlock something much greater, a way to explore structures in the universe that cannot be detected by any other means. Fast radio bursts are shifting from curiosities to precise measuring tools. Each one carries a signature of the electrons it passed through, effectively recording the density of matter along its path. By detecting bursts from many directions, astronomers can build a map of matter that does not emit light, including the sparse gas between galaxies. Over time, patterns could reveal the structure of the cosmic web itself. Stitched together from ancient signals, a single burst, lasting only milliseconds, could fill a gap in that map. Somewhere above us, the next one may already be traveling through the darkness toward our instruments. What if everything we thought we knew about the universe's future was wrong? Since the late 1990s, dark energy has been the invisible engine pushing space apart faster and faster. But new DESI data suggests it's not constant. It might be losing strength over time. Watch closely, because if this holds, it won't just change textbooks, it could change the ultimate fate of the cosmos. In 1998, two teams studying distant supernova noticed something that didn't fit the picture. Astronomers had been building for decades. These exploding stars, acting as cosmic mile markers, appeared dimmer than expected. That dimness meant they were farther away than models predicted. And the only way to explain it was if the universe's expansion was speeding up. It was a sharp break from the long-standing expectation that gravity should be slowing expansion over time, instead of a universe coasting to a standstill or collapsing inward in the far future. The data hinted at a cosmos being pushed apart faster and faster. To make sense of this, scientists looked back to an idea buried in the pages of early 20th century physics, Einstein's cosmological constant. When Einstein first introduced it in 1917, it was a kind of mathematical fix, a term that counteracted gravity to keep the universe static, which was the accepted view back then. When later observations revealed that the universe was in fact expanding, he dropped the constant entirely, dismissing it as unnecessary. The 1998 discovery gave that discarded term a second life. Now, instead of balancing expansion, it became the explanation for a mysterious repulsive force accelerating it. The modern version of that idea imagined the vacuum of space itself as holding a constant energy density. This meant that as space expanded, more of this energy appeared, making the repulsive effect grow in influence over time. It was simple in form and fit the data remarkably well. For over 20 years, this constant vacuum energy, what we now call dark energy, sat at the heart of cosmological theory. The scale of its role was immense. Matter, the stuff that makes up stars, planets, and living beings, accounts for less than a third of the universe's total energy budget. Dark energy makes up about 70%, dictating not just how galaxies move apart, but shaping the entire long-term trajectory of cosmic history. With such overwhelming influence, it became the dominant term in our equations and the dominant concept in our teaching. Students learned a picture in which dark energy had been present in exactly the same density over billions of years, untouched by the expansion of the universe it powered. For a time, that stability felt like closure. Textbooks fixed the cosmological constant alongside other fundamental features of the universe, and research turned toward measuring it more precisely rather than questioning whether it could change at all. It was the kind of neat, consistent result science doesn't always get, and for many, it seemed like one of the rare cases where the big picture had settled. But in science, settled pictures are often temporary. Even the most firmly placed ideas leave room for testing, and the most telling challenges often hide in the smallest details. Precision measurements are the pressure tests of physics, and subtle deviations, when they show up more than once, can threaten the foundations they probe. What happens if the vacuum energy isn't constant after all? Could the force driving acceleration slowly weaken or grow stronger over time? Such a possibility wouldn't just tweak our numbers, it would reshape major predictions about the universe's distant fate and force a rethink of fundamental physics. The cosmological constant rose from a discarded term to the guiding explanation of an accelerating universe. If fresh evidence is now putting that status into question, the change would land at the heart of our understanding of cosmic evolution. And today, a new generation of instruments has the sensitivity and reach to look for those cracks. Among them is one of the most ambitious galaxy mapping projects ever attempted, capable of stretching our picture of the cosmos to its limits. How can measuring where galaxies sit in the universe today tell us if dark energy might be running out of steam? The answer lies in tracing not just positions in space, but their arrangement across billions of years of history. That is what the Dark Energy Spectroscopic Instrument DESI was built to do. DESI is mounted on a telescope in Arizona, but it's no ordinary camera. It uses 5,000 robotic fiber optic eyes, each aimed at a specific galaxy or quasar. Every night, this network tracks the faint light from millions of these objects. Over its survey, DESI will gather spectra from about 15 million galaxies and quasars, each spectrum carrying information about both distance and motion. In effect, it's not just taking a snapshot, it's building a time-lapse of the cosmos. Because light from distant galaxies has traveled for billions of years, looking far out means looking far back. DESI's reach extends up to 11 billion years into the past, capturing how structures in the universe grew over most of its history. By combining these distances with angular positions on the sky, it can construct an enormous 3D map larger than any assembled before. This map doesn't just show where objects are, it preserves subtle patterns imprinted at the dawn of time. One of those patterns comes from baryon acoustic oscillations, ancient sound waves that rippled through the hot plasma of the early universe. When the universe cooled enough for atoms to form, these waves froze in place, leaving a preferred spacing between clumps of matter. That spacing now acts like a cosmic ruler. As the universe expands, the distance marked by that ruler stretches, and the rate of stretching depends on the behavior of dark energy. DESI reads this ruler by examining the redshifts in its galaxy spectra, the way light stretches toward longer wavelengths as its source moves away. By comparing the apparent sizes of the BAO spacing at different points in time, cosmologists can track how the expansion rate has changed. If dark energy were truly constant, the data should line up neatly with the cosmological constant model. This was the expectation going in a confirmation of the steady, unchanging vacuum energy that had fit so well for over 2 decades. Instead, something more complicated emerged. When DESI's measurements were analyzed alongside cosmic microwave background data and supernova distances, the model that gave the best statistical fit was one in which dark energy varied over time. The numbers aren't strong enough to call it a discovery. The statistical weight is significant, but doesn't reach the conventional threshold scientists use to declare a result confirmed. That makes it the start of a conversation rather than the end of one. Still, the pattern is intriguing because these independent probes, CMB, supernova, and now BAO mapping are all sensitive to different parts of cosmic history. And yet they converge on the same hint. If this trend is real, dark energy might be like a cosmic engine whose fuel supply is slowly running down. As the fuel fades, the push that drives galaxies apart would weaken, changing not just the pace of expansion, but the ultimate shape of the universe's story. A constant force leads to one set of futures. A diminishing one opens the door to very different outcomes, including possibilities where acceleration stalls out entirely. For now, the evidence remains provisional. But DESI has shown that the tools exist to measure these shifts with precision unthinkable in the 1990s. And if the next round of data strengthens the case, it won't be a minor adjustment to our equations. It will mean the universe's future path might not be the one we've assumed for a generation. DESI's results are more than an adjustment to a parameter. They hint at a different story, for the universe itself. If dark energy is truly weakening, expansion might not continue forever. Over immense time scales, it could slow, stop, and even reverse, ending in a collapse known as a Big Crunch. The next verdict comes with new observatories: Euclid, the Vera C. Rubin Observatory, and NASA's Nancy Grace Roman Space Telescope will extend these measurements. They may confirm a constant, unchanging energy or reveal that it changes with time. In cosmology, even ideas that seem permanent can shift when the map becomes clearer. 8 billion years ago, the universe exploded into existence. That's what we're told. The Big Bang is the beginning of everything. But what if it wasn't? What if there was a before, a chapter of reality hidden beyond the reach of telescopes? Beyond even the boundaries of space and time we understand. We'll pull back the curtain on the Planck epoch, a realm so extreme that even our best physics collapses. And here's the catch: the answer to what happened before might not just be unknown, it might be unknowable. Physicists can reconstruct the chain of events leading back to the earliest split seconds of the universe's history. They can map the faint afterglow of the Big Bang. They can trace the formation of the first atoms. They can even calculate what happened in the first trillionth of a second. But go back further to a mere 10 millionths of a trillionth of a trillionth of a trillionth of a second after T0, and the trail stops abruptly. The equations that describe reality reach a wall that refuses to yield. That unyielding wall is called the Planck epoch. It lasted only 1043 seconds. But within that instant, the universe as we think of its space, time, physical laws may not have existed in any recognizable sense. Temperatures soared to more than 100 million billion degrees. All known forces could have been merged into one. The density was so high that a pinhead of that early universe would outweigh entire galaxies. Our current theories, which work so well in explaining stars, galaxies, and even black holes, break apart here. This breakdown has a specific fingerprint: infinity. The numbers in the equations spike to unbounded values. The curvature of space goes to infinity. Energy density goes to infinity. Temperature goes to infinity. In physics, such infinities are not majestic truths. They are red flags. They tell us the mathematical model has been stretched beyond its valid range. The picture becomes meaningless, not because the universe stopped behaving, but because our description stopped making sense. On the scale of the Planck epoch, quantum effects of gravity dominate. Just as quantum mechanics is essential for understanding atoms and molecules, and general relativity is essential for understanding planets and galaxies. Both theories must operate together here. The problem is, they do not cooperate. Gravity resists being quantized. Without a consistent theory of quantum gravity, we cannot even say for certain that space-time, as a smooth and continuous fabric, existed in that first instant. It may have been granular, chaotic, or replaced by something without any analog in our everyday experience. Imagine an ancient map of the world, its coastlines neatly sketched until you reach a brown corner labeled with creatures never seen, marked simply as "Here be dragons." The Planck epoch is our cosmology's blank corner. Beyond it might lie unknown physics, but whatever is there could contradict some of the foundations we take for granted. Many cosmologists agree to explore further back in time. We first need that missing theory of quantum gravity, a framework that merges the rules of the very large with the rules of the very small. Efforts toward string theory or loop quantum gravity are attempts to build this bridge. Without it, The deepest questions about beginnings cannot be answered. Even ideas that stretch our timeline, like cosmic inflation, run into a limit. The Border-Guth-Vilenkin theorem shows that, under general assumptions, any universe that has been expanding throughout its past cannot be extended infinitely backward. Inflation might push the moment of origin earlier, but it cannot erase it entirely. This hints at a definite, if inaccessible, point where our universe began. Whether that point represents creation from nothing or a transformation from some prior state, we cannot yet say. Right now, physics meets a hard stop at the Planck wall. What lies before it could be the grandest chapter of the cosmos or no chapter at all. So if our current understanding fails here, what kinds of radical ideas are scientists turning to in order to find a way around this barrier? What if the Big Bang wasn't the true start of everything, but simply the latest link in a much longer chain? In this view, what we call the first moment might only be a transition point, the latest chapter in a universe with a far deeper history. That question has driven physicists to design theories that try to move past the Planck wall without discarding the rules of physics entirely. These aren't fantasies, they use real mathematics and in some cases produce predictions we can hope to test. But stepping beyond the Big Bang is also where science begins to tread near the border with speculation. One of the most striking ideas is Roger Penrose's conformal cyclic cosmology. In this model, the universe doesn't have a single lifespan. Instead, it moves through eons, enormous spans of time that begin with a Big Bang and end when the last black holes evaporate. In the very far future of any given eon, the universe becomes empty and cold, with no massive particles left. Without mass, the concept of time and distance can be mathematically reshaped until the whole expanse folds into something equivalent to a hot, dense state again. That state becomes the Big Bang of the next eon. In this framework, nothing at the end is not an absence, but a special type of space-time that can transition smoothly into something without a point of infinite density. Every aeon leaves subtle imprints on the next, potential signals that might appear as faint patterns in the cosmic microwave background. Another scenario starts not with the far future, but with the collapse of something much larger. The black hole bounce theory proposes that our universe could be the interior of a black hole that formed in a parent universe. Instead of ending in a singularity where physics breaks, the intense compression triggers a rebound, a quantum bounce that becomes an expanding universe on the other side of the event horizon. In this picture, what we saw as the Big Bang was really the flip side of a catastrophic collapse. If true, the laws of physics inside extreme gravitational fields might be the same bridge that links one universe to another. Observationally, some researchers suggest tiny variations in cosmic structure might reveal hints of such a process. A different approach, the so-called Wi-Fi model, connects the mystery of before to one of the biggest questions in current cosmology, the nature of dark matter. In this idea, certain particles of dark matter could have been created during inflation, the ultra-rapid expansion phase of the early universe. If these particles formed before inflation ended, they might preserve information about conditions that predate the Big Bang's hot phase. Identifying such particles would be challenging, but not impossible, and experiments already planned for the coming years could put the idea to the test. These theories also inspire specific searches. Space missions like a rocket's aim to map extremely faint halos around galaxies, possible relics of processes from an earlier phase. Measurements of the curvature of space could provide another check, Several of these models predict slight deviations from perfect flatness, leaving a lasting footprint that astronomers might detect with next-generation surveys. While they offer different narratives, the appeal of these blueprints lies in the fact that they don't just imagine a before. They suggest experiments, observations, and data that could prove or disprove them. The next decade might offer the first clear evidence for or against the existence of a time before the Big Bang. And yet, even if one of these ideas breaks through our current limit, it may only shift the question to a deeper layer, one step further back from the place we thought was the beginning. The story of the universe's origin is not finished. It remains an investigation at the boundary of what humans can know, where our best tools still fail to reach. Even if we find evidence for events before the Big Bang, the nature of time and cause may break down, making the idea of a first moment meaningless. Each new answer risks opening a deeper question, with no final origin in sight. The next discovery could shift our entire perspective, not just on how the universe began, but on whether beginnings themselves are a fundamental part of reality or an illusion